Okay, does everybody have a copy of the notes? And any more submissions of that water hammer problem? Got all the water hammer here? Okay. Well, on Wednesday are the pump problems. We're going to do a couple more pump examples in class today to help you out with that assignment. And then on Wednesday for the lecture, actually, I'm going to be introducing the first part of the design project for the course. And so that will, not introducing any new content that will be on the exam on Wednesday. The end of today's lecture and the homework assignment you're going to submit on Wednesday is included in the exam, but then the design project stuff we talked about on Wednesday won't. Bring that equation packet, and there may be a few extra equations that I include either on the exam or in a separate handout for Friday. And we may have something that you would be best off solving using Excel, so you can bring your own laptop or use the tablet PCs if you want to work on those for the computer problem, if we have one. Any questions about that? All right. Speaking of the equation packet, if you've taken a look in there, you'll notice that the pump power equation looks a little bit strange. They're using different symbology than we've seen in some of the equations. And so they are, instead of saying power is a P, power is W dot. I think that's maybe some symbol that's used with thermodynamics. Some of you are in that class. And efficiency is built into the equation there. This is talking about the pump power that's going to be used to move water from place to place. And so you'll notice they're dividing by the efficiency. And so if you've got a pump that is not 100% efficient, remember you're going to have to distinguish between the energy or the power that's going into the pump and the power that's applied to the water. And so I just wanted to point out that the equation in the equation packet looks a little bit differently than we've seen it. Also, for the homework assignment that's due on Wednesday, I wanted to give you a couple of tips. Problem 924, they don't actually give you the equation for the pump. They tell you the equation, I think, the system curve, but the pump curve isn't given to you directly. There's a figure with which you're supposed to find the pump curve. You'll be estimating the constant that's in front of Q squared. And so I think you can substitute in a couple of values and see if the figure that you come up with looks similar to the figure that they presented. In fact, you could, using Excel, put together a graph really easily of different C values and trying to find what is the pump curve that you should use. And then, of course, to find the operating point, you set the pump curve equal to the system curve and solve for the flow rate. So just a hint there for problem 24. And then problem 27 is a cavitation problem. We're going to talk about cavitation today, but it refers back to problem 923, which isn't included in this problem set. And so I wanted to give you some of the information from problem 923 that you would have had if you did solve it. That'll save you from having to do both problems. Those values that are shown there you can use in problem 927. All right. I mentioned previously that there are these manufacturer-provided pump curves that talk about performance, and there are a couple of elements I wanted to show you on this pump curve. First of all, on the y-axis, it's talking about the total head that a pump is able to produce, and you see that as the flow rate increases, that the total head decreases. And these are curves, the typical characteristic curve that we looked at in class previously had a certain cutoff head, and that's the amount of head that the pump can generate at zero flow rate. And you'll notice that this particular pump, they've provided different curves for different rotational rates. And so if you pump this with a motor that's rotating at 3,200 RPM, you can see what the pump curve is, 2,800 RPM, and so on. The next thing I want to point out are these curves, 50, 55, 60. These are efficiency curves. And so you can find out the relationship between the energy that's going into the pump and the energy that it's providing to the water by looking at what location you're on in terms of a certain flow rate and a
certain pump head that's being provided, you can find out how efficient it is. And so that would give you an idea of the electrical requirements that may be needed. These lines refer to the power. You can see 40 horsepower, 50 horsepower, and so they've already sort of graphically solved the power equation for a certain pump head, for a certain flow rate, and they're assuming a unit weight of water in order to calculate those pump powers. And then the final thing here, you see NPSH, and that stands for net positive suction head. And what it's referring to is the amount of head that's required in order to avoid cavitation. And the relationship is that as the flow rate increases, you can see over here on the right side of the curve, the flow rate is at its highest, more net positive suction head is required. And so we're going to talk about what that means, but the general trend I want you to notice is that for low flow rates, you don't need as much net positive suction head. There's less of a risk of cavitation at a low flow rate than there is at a high flow rate. And so there are curves that are very similar in appearance to this by all the manufacturers and show the operating conditions of pumps under a whole wide range of possible flow rates and pump heads that they may face. And so we'll talk about this net positive suction head and what are the factors that relate to it. We've spoken before about vapor pressure and how when water boils, that's an indication of either the fact that the temperature has been elevated up to the vapor pressure, up to atmospheric, where the vapor pressure and the atmospheric pressure are equal by either elevating the temperature of the water to increase the vapor pressure, or you can decrease the pressure of what surrounds the liquid until it starts to boil. And so these little bubbles here that are inside of boiling water, they're not air bubbles, they are H2O bubbles. That's water vapor that is inside of there. And the same thing is true in a pump that's cavitating. It's not that there has been some dissolved air that's coming out of solution. It's actually the liquid that's volatilizing and boiling during cavitation. And so this curve is showing the relationship graphically between temperature and absolute pressure of water, the vapor pressure of water. The typical boiling point, 100 degrees Celsius at 760 millimeters of mercury. That's the sea level boiling point of water. At higher elevations, where there's less atmospheric pressure, then water boils at a lower temperature. And remember that when water is being sucked from a reservoir up into a pump, the pressure is always decreasing in the direction of flow. And so the risk that we're facing when we are moving water from the suction side of the hose into the pump is that the pressure will get too negative, that in gauge terms it's negative. Of course, the absolute pressure is never negative, but a negative gauge pressure gets us closer to the vapor pressure. And so the graph, the figure that we saw previously was that here's a free surface of water, and water is flowing in the direction towards the pump. The pressure is constantly decreasing in the direction of flow, and so the pressure is getting more and more negative. And it's actually inside of the pump that the situation is most precarious, because the impeller has a curved vein, several curved veins inside, and as it accelerates the flow through the pump, there are very high pressure side of the pump and a low pressure on the back side of the vein. It's a little bit like an airplane wing, so that there are huge pressure differentials inside of the pump. And so the cavitation can occur inside of the pump even though the rest of the bulk liquid may be far away from the vapor pressure. You know, it might be that the vapor pressure for water at set 20 degrees Celsius, so 17.5 millimeters of mercury, it may be that you're not even close to being that low in terms of the absolute pressure in the suction side of the pump pipe, but when you get inside of the pump, because of the huge differences in pressure at the actual impeller, that's where the cavitation will form. And so the reason why they have these specified amounts of net positive suction head is they know inside the pump what's happening when you've got 550 gallons per minute going through the pump. And so these varying levels of net positive suction head that's required is because they have an understanding of what the relative pressure differential is inside the pump itself. And so the vaporization of liquid into a gas inside of the pump is what can cause the cavitation. And you may think that these tiny little these tiny little vapor bubbles, how much trouble could they cause? But they can collapse when they finally get to the pressure side of the pump, and the jets, the very small jets and turbulence that the collapsing bubbles cause can have localized velocity gradients up to 110 meters per second. 800 megapascals have been measured. And just by comparison, of course, the water that flows through a pipe under the roads of a city is generally less than 1 megapascal. And so the 800 times the pressure, although it's a very small localized increase in pressure, it can be quite damaging. And so we're going to take a look at a couple of videos of cavitation. Hopefully these play. These are high-speed camera recordings. This, I know it's hard to see, but this is an impeller as it rotates through the water. Let me play it another time. So it's a rotating impeller, and it's showing the vaporization of the liquid as it rotates. The impeller rotates through the water. No, this one doesn't seem to play. Let me see if I can play it with. I wonder if they've got VLC on here. No, it's a pity. Let me just try one more time. Oh, here it is. It almost looks like miniature explosions as the impeller rotates through the water. There, if you think about what's happening on a wing, remember the Bernoulli's effect for a wing is that on the top side of a wing there is low pressure, and on the bottom side of a wing is high pressure. And that's what gives lift to a wing. The Bernoulli's effect is because for some packet of air that gets split by the wing, some of the air is going to travel over the top, some of the air is going to travel under the bottom, and they both reach each other at the same time because of continuity. You can't have air accumulating below or above the wing, and so it reassembles itself at the end of the wing, but this is a longer distance along the top than on the bottom. And so it's the shape of the wing that causes relatively low pressure because it's high velocity, and on the bottom of the wing, high pressure and relatively speaking, low velocity. And if we go back to the curved shapes of impellers, we can see that there's that same potential in a centripetal pump. So you can see that same curved shape inside the pump. The impeller is going to have on the outside of the pump a low pressure, and on the inside of that impeller blade a high pressure, and it's the low pressure location that has the risk of cavitation. Here's a close-up of an impeller that's been damaged due to cavitation. Caused pitting and flaking of the material. So we want to avoid it. And the way that we can know how close we are to this risky condition of cavitation is by calculating the available net positive suction head. And the terms here start off with the pressure. This P naught is the pressure of the atmosphere, and delta Z sub S is the suction side elevation difference, and so that's the difference between the reservoir and the elevation of the pump. H sub L sub S is the head losses, both friction and local losses on the suction side of the pump, and then the P sub V is the vapor pressure. And what this answers is how far the system is from cavitating. If you have a big NPSH, that means it's very far from cavitating, that there's no risk of cavitation. But the bigger, a smaller NPSH, as it gets closer to the required net positive suction head, then the risk of cavitation increases. All right. And we do all these calculations in absolute terms because the vapor pressure of the water is going to be in absolute terms, and so we have to express the pressure of the atmosphere in absolute terms as well. Required net positive suction head increases with increasing flow rate. That's what we saw on those manufacturer-provided pump curves, how much pump head is required for a certain operating condition. And so we're going to be doing a comparison of the requirement to what's available. And if the amount of head that's required is bigger than what's available, then cavitation occurs. And so this is the bad scenario, where required is more than available. But if available exceeds the requirement, then it's fine. There is no risk of cavitation. And cavitation just barely starts to occur. The term is incipient cavitation when the two are equal. And so if you want to find out like the maximum suction side length, for example, of a pump hose, then you would set the available equal to what's required and solve for what conditions are going to make it so it's just barely starting to cavitate. In the system that's shown here, we know that the pump requires 3.5 meters of net positive suction head. That's a value that was looked up off of a manufacturer table for the flow rate in question. And so what we want to do is find out if cavitation occurs here. And what I'd like you to do is substitute in atmospheric pressure for the reservoir surface here. So P naught is just 101,325 pascals, typical sea level atmospheric pressure. You can see the elevation difference for the suction side. And then we're told that the suction side head losses, including the local loss at the bend, the entrance loss, and the friction losses, total 1.6 meters. And then for the water temperature of 40 degrees Celsius, we have a certain vapor pressure and a density that's known. So calculate the available net positive suction head and compare it to the requirement. Well, let's think about what things are going to increase the probability of cavitation. You can see that the available suction head starts off with atmospheric pressure divided by the unit weight of the fluid. And so that's approximately 10 meters of available head to begin with. Any of the other terms are going to decrease the amount of suction head that's available. And so the delta Z sub S, if you have a big elevation difference between the liquid surface that's being pumped from and the pump, that's something that can increase the risk of cavitation. And that's why pumps will usually be pretty low relative to the water surface. If you have one reservoir and water is going up to another reservoir, they wouldn't put the pump right there. More typically, the pump would be close to the origin rather than the destination. And from an energy standpoint, if you're just looking at the energy equation, flow from 1 to 2, the energy equation is sort of blind to that. The location of the pump being here versus there isn't going to change the friction losses. It's not going to change the local losses. The velocity wouldn't be any different. It's just really a matter of avoiding cavitation. Because, for the water flowing a certain velocity, the friction losses on the suction side and the pump side, the pressure side of the line, aren't
affected by necessarily what the pressure is. It's the velocity that determines the friction losses. And so, okay, that's the first thing, is the location of the pump, vertically speaking, delta ZS. This next thing, head losses. So what's going to promote risk of cavitation is a really long suction side hose, because remember that for friction losses, H sub F is FLV squared divided by D2G. And so what promotes a risk of cavitation would need to be a rough pipe and or a long pipe, high velocity, small diameter. And so a small diameter and a high velocity go hand in hand. And so more typically, they'll have a large diameter pipe going from into the suction side of the pump. Large diameter reduces the velocity, also means for a large diameter. And you want to make the length of the pipe as short as possible and relatively smooth as well. And then the other thing, what other thing favors cavitation is warm water, because the warmer the water is, the higher the vapor pressure will be. And so that will also be another thing that's subtracting from the available. And so we want there to be a big available head, and so we want to minimize these three things that can reduce the suction head that's available. And then the other part of the equation, of course, is picking a pump that has a low requirement. And let's go back and take a look at this pump curve. You see the maximum here is 30 feet. That corresponds approximately to the 10 meters. That 30 feet of water is about the maximum that would be available. And so if there was any greater requirement, this pump would never be usable. And so they wouldn't show like 40 feet of net positive suction head required, because it wouldn't be possible. The only way it would be possible is if you were starting from a pressurized tank, if you were pumping from a pressurized tank. But that's sort of the upper end of what would be considered a legitimate required suction head. And so you'd need to maybe flip through a book if you knew that your situation had only 3.7 meters of suction head available. Then you may have to flip through several different pumps to find the right combination of head production capacity along with flow rate and the suction head requirements. And then, you know, the other aspect of it is finding an operating point that matches the electric motor that you'd like to rotate at. So there's a lot of considerations there. Any questions about cavitation and how to compare the suction heads? Okay. The next thing we're going to talk about today are affinity laws. And these affinity laws come about because there are combinations of pumps. Sometimes rather than just having a single pump, you may have pumps working in parallel or in series, and sometimes pumps come from a manufacturer and have a similar family of styles. You can see the two pumps that are shown here have a similar shape. It's just that the pump in the background has a larger diameter of the outlet than the pump in the foreground. And there are these mathematical relationships that equate how switching out a certain pump and replacing it with another pump is going to affect the head loss that's available. I'm sorry, the pump head that can be generated, the rotation rate that's needed, and these affinity laws can also be used to tell you what the performance will be if you replace a single pump with two pumps. And so if you had water flowing and then it branches and goes through two pumps, the affinity laws can tell you how the performance compares, and then it comes back together again and goes out, versus if you had the pumps in series rather than in parallel. This is parallel. This is series. I spell series wrong. Series. No. Parallel, series, and then the other possibility is just switching a pump
with a pump of a different size and wondering how is it going to behave. And these affinity laws are a little bit like the dimensional analysis things that we did in fluid mechanics, where you're trying to equate the performance of two related things. It's very similar to maintaining similitude and having a prototype and a model. And so there's a discharge coefficient and a head coefficient. And you can put in the system curve and the pump curve into these relationships and the corresponding characteristics of the pump, like what the pump's diameter is. And then you can find out for a certain rotational rate what the pump head is going to be for this other kind of pump. And so let's take a look at an example. That's the most useful way of understanding how to apply the affinity laws. Ordinarily, there's a pump where a 1200 RPM motor is being used, and it's got an 8-inch impeller, and we've got a performance curve there. And what if we're going to use a variable frequency drive to adjust it from 1200 RPM to 2400 RPM? So we want to find out the new performance curve with a different rotational rate.
Does omega need to be in radians per second?
It doesn't, because we're going to be canceling out. It'll end up being a ratio. That's a good question. You can convert it to radians per second, but you can leave it in RPM since it's going to be a ratio of rotational rates. Okay. So originally we have an equation for the pump performance. And this is for a rotational rate of 1200 RPM and 8-inch diameter. And we're wondering what will happen when the same pump is rotated instead of at 1200 RPM. We're going to take the same pump and rotate it at 2400 RPM. So we're going to say that the original rotation rate is 1200. So this and our after will be 2400. We can rearrange that. Since we're not changing the diameter on this, it's the same pump, but it's just operating at a different point, we don't have to use the D term. We can just, D1 and D2 are equal in this first example. All right, we now have a relationship of the flow rate of 1 to the flow rate of 2 and a relationship of the pump head of 1 to the pump head of 2. Our original pump curve was HP is 12 minus 0.1 Q1 squared. So we substitute in, this was HP1, and it was the flow rate originally, so Q1. Now we substitute in 0.25 HP2 in place of HP1, still the 12 minus 0.1, and substitute in 0.5 Q2. This was the relationship between the flow rate 2 and flow rate 1. And if we solve for HP2, we'll get 48 minus 0.1 Q2 squared. So it quadruples the cutoff head from 12 to 48 meters. Yeah. So that's the new performance curve at 2400 RPM. So what I'd like you to do now is use the same 1200 RPM motor, but what if they went from the 8-inch diameter impeller to a 10-inch diameter impeller? So make the same kind of substitution into both sets of equations and find out what will be the new performance curve with a 10-inch impeller. Relatively speaking, in the first example, this first part where we were increasing from 1200 RPM to 2400 RPM, what was the benefit for doing that? Like, what's the good thing you get out of doubling the rotational rate? How was the original pump curve different from the modified pump curve when we went from, this was 1200 RPM, and this was the one, same pump, but operated at 2400 RPM.
Quadrupled the cutoff.
What's that?
Quadrupled the cutoff.
Yeah, the cutoff was much higher. And so what that means is you can pump water to a higher elevation. The highest you could pump water to is an elevation of 12 here. And that's actually at just a trickle of a flow rate. If you actually have a non-zero flow rate, then it's going to be less than 12. Here, by doubling the rotational rate, you get 4 times the cutoff head. So think about in terms of benefit. What's the benefit to going from an 8-inch impeller to a 12-inch impeller? What's that? Well, you can get a whole variety of flow rates through either pump, but it's related to flow.
You're losing less per flow.
Precisely. So if you look at this 0.1, what this 0.1 in the original, 0.1 in the original pump curve meant was that for every unit of Q, you're losing 0.1 meters or feet. I guess this is probably feet, and this is inches of inch diameter pumps, so we'd say it's feet. So anyways, the rate of energy loss due to increasing the flow rate is much larger than when we've got a bigger diameter impeller. You're not losing your pump head as quickly. And it looks like there's a larger cutoff as well. But if someone said, we need to, here's the original pump situation, you know, we've got the original pump curve and it's 1200 RPM, 8-inch impeller, and we need to pump water 30 feet. Should we increase the rotational rate or get a larger diameter pump? In this case, it would be, if you needed to pump at 30 feet, you'd have to go with increasing the rotational rate, because increasing the diameter of the impeller does increase the cutoff head, but not quite as dramatically as increasing the rotation rate. So, nonlinear relationships. That's the affinity laws. Any questions about the example? Okay. Just a quick review of different terminology we use sometimes to talk about similar things. Energy, we've listed the energy equation here, measured in joules. It's sort of the base unit for measuring energy.
We oftentimes will refer to energy, though, in terms of meters of fluid. In the energy equation here, each of the terms, the pressure head term, the velocity head term, the elevation term, pump head, turbine head, head loss, all those have units of meters. So you can express energy in terms of joules or in terms of meters of water. It's like meters of water is sort of expressing it in terms of a potential energy. Work is a joule where work is a force, Newton, which is applied over a length or distance, meter. And in fluid mechanics, we talk about shaft work, which is the head that's supplied by a pump or given up to a turbine. And same units between energy and work, and same meters. If we had meters of energy in the energy equation, then you can have a pump doing work to add additional energy to the energy equation, or a turbine is going to be taking work from the system. And usually in terms of the way we use these words, energy is used to perform work, even though they have the same units. And then power is where we add a time dependency in there. It's the number of joules that are being expended or supplied per second. So that's units of watts. The power equation, we've looked at it already today, the form of it that's listed in the equation packet, which is for the FE review manual, but assuming 100% efficiency, it's just the flow rate times the unit weight of water times the pump head, if power is being added to the water. So here is the pump output power. If we're thinking in terms of the traditional units, of course, there's 550 foot-pounds per second per horsepower, and the pump equation, the pump curve that we were looking at before was listing the power in terms of horsepower. And if we're talking about the pump input power, it can also be related to the shaft speed and the torque. And so there's another formula that I don't know if you'll end up needing to use it for this assignment. No, you don't. I don't think you need to use it for the assignment, but just wanted to point out a couple of additional equations that relate to ways to calculate efficiency or calculating power. That is it for today's lecture. If we just look at these announcements one last time, a good way to study for the exam is to just go through the homework assignments and see where the mistakes were. Let me know if you've got any questions on this one that's due on Wednesday. In fact, since you won't have it graded before the exam, I'm more than happy to tell you if you got the right answer. If you have any uncertainty, you can stop by and ask me if you've got the right answer, so that you don't have any question about whether you understood those pump problems. But with that, we will talk about the project on Wednesday. I'll see you then.